Okay, so today what I'd like to do is to bring out a lot of connections. First between the gamma function and Gaussian integrals. Then I'd like to talk about the Mittag-Leffler representation for the gamma function, which I mentioned briefly the last time. After that, I'd like to talk about the log derivative of the gamma function, which too I mentioned last time, derive a few of its properties, and then give a very important couple of identities satisfied by the gamma function, which are extremely useful. One of them is called the reflection formula, and the other is called the doubling formula, very useful things. And after that, I'd like to introduce the beta function and derive the connection between the gamma function and the beta function. And we take it from there. So the first item is Gaussian integrals. And as all of you know, the general Gaussian integral the familiar one, the one we are most familiar with, is this integral, 0 to infinity du e to the minus au squared u to some power r. This integral is going to converge as long as real A is positive, so that this provides a damping factor at infinity, and one should also ensure that this does not provide a divergence at the origin, so you also require that r be greater than -1, okay, so that it does not diverge at either end, and that is the general Gaussian integral. Okay. Now what is the way to do this? Well, substitute, put au squared equal to t, or u equal to root of t over root of a, and then du is dt over 2 root of a root of t. So the integral becomes equal to 0 to infinity dt over 2t to the half, there is an a to the half here, e to the minus t, and then a u, which is t to the power r over 2 over a to the power r over 2. So that is 1 over 2 a to the power r plus 1 over 2, and integral 0 to infinity dt t to the r over 2 e to the minus t, and that of course is a gamma function, the original representation for a gamma function. So it immediately says that this integral equal to gamma function of r over 2 plus 1 over 2 a to the r plus 1 over 2. So it right away provides you with an expression for this general integral in terms of gamma functions. Okay. Now one can generalize this further, we can put a linear term here, etc., and then complete squares and so on. If it is minus infinity to infinity, then you can translate, shift the integral, still remains by any constant amount, but if it is 0 to infinity, you will end up getting error functions of various kinds. Okay. So we will not go into that right now, but I just wanted to point out that this integral is doable or writable in terms of gamma functions here. In particular, if you set r equal to 0, this thing goes away, and then you have e to the minus au squared, which is gamma of 1 divided by 2, and then there is a to the power half out here. There should be some is it gamma of r plus 1 by 2? Pardon me?
T to the power r minus 1 by 2.
T to the half in this term.
T to the power here, is it? Ah yes, that is right, yeah, because otherwise it becomes independent of, I was wondering where this went, yeah, t to the power of r over 2 minus a half, thank you, yeah. Okay. And then what does the integral become? Gamma of r minus 1 over 2 r plus 1 over 2. Yeah, thank you. Okay. So this immediately implies for instance that integral 0 to infinity du e to the minus au squared equal to gamma of a half, which is square root of pi over square root of a. Now this integral of course you can do by other tricks. You can do this by squaring this. This was a famous trick that Poisson discovered way back in the early part of the 19th century. You square this in order to find I squared, go to polar coordinates, and then you come back and you discover this integral is square root of proportional to square root of pi, and then the scale factor is 1 over root a. Okay. Now the immediate consequence of this is that you can start writing what the gamma function is for half odd integers. So gamma of half equal to root pi, gamma of 3 halves is half gamma of half, which is equal to half root pi, gamma of 5 halves equal to etc. etc. There is a 3 halves, so it is 3 quarters root pi and so on. So all the half odd integers you can write down in a closed form in terms of some factorials, and then finally there is a square root of pi factor, and you can go backwards in the other direction also. So for example we have minus half gamma of minus half equal to gamma of half, which of course implies that gamma of minus half equal to minus 2 root pi and so on the other side. So you have the possibility of writing gamma functions of half odd integers in terms of some simple numbers, etc. Not so easy to do it for other values of rational values of the argument, but certainly for half odd integers this is a very useful formula. This appears all the time, very familiar thing. Okay. So now let us go over to the Mittag-Leffler representation for the gamma function. Now what is it we know about this function? We know that gamma of z is a meromorphic function. It has simple poles at all non-positive integers, and at z equal to minus n the residue is minus 1 to the n over n factorial. So what we need is a formula which writes down the gamma function in terms of a sum over all these poles with the corresponding residues plus a piece that is an entire function. And now if you go back and ask what's the singularity due to, eventually it arises because you had t to the power z minus 1 e to the minus t. It arose from here, from this factor here, right. So all we have to do is to write this as an integral from 0 to 1 dt t to the z minus 1 e to the minus t plus an integral from 1 to infinity in this fashion, and do this integral explicitly. We do this by integrating by parts, for example, and then what do you get? The first term, what do you get here in this integral if you work this out? So integrate this and differentiate the other part, etc., and eventually you are going to get, once I write this, well the next step is to say alright, let us expand this e to the minus t in powers of t. So this becomes equal to summation n equal to 0 to infinity 1 over n factorial, and then I do t to the z minus 1 e to the minus t, which I have expanded as t to the n over n factorial. So there is a minus 1 to the power n here, and an integral from 0 to 1 dt t to the power n plus z minus 1, which of course gives me a 1 over z plus n, and that is it. Plus a portion which is 1 to infinity dt e to the minus t t to the z minus 1. So we have what we want. This is the Mittag-Leffler representation. Series representation for gamma of z. Here are the pole terms with the corresponding residues and that portion is an entire function of z. It has no singularities in the finite part of the z plane. Okay. Now tell me, I broke this up as 0 to 1 and 1 to infinity, but I could have really broken it up as 0 to any a and a to infinity, where a is any positive number at all. Why didn't I do that? Why did I choose 1 here? What would happen if I chose an a, some other a? Whatever remained would still be an entire function, as you can see, but why didn't I choose an a? Pardon me? Yeah, I want a series expansion in terms of the poles, the pole terms, the precise pole terms with the correct residues. Had I chosen some a, that factor, there would be factors of a here sitting here. Those would not appear in the residue. Those are not the real residues. So this choice is the only one that gives you the correct residues at these points. Okay? So you have to watch out, and that is what determines what this entire function part is. Okay? Okay, now that we have this representation, let us go on to look at some of the other properties of this gamma function. And one of them was, I needed to remind myself, yeah, we needed to define the log derivative. So I defined psi of z equal to d over dz of log gamma of z. Okay. That was a log derivative, and recall that you have a functional equation gamma of z plus 1 is z gamma of z, which will of course imply, if I take the logs on both sides and differentiate and divide by the appropriate gamma function, this is going to be psi of z plus 1 equal to, on this side there is a 1 over z plus psi of z. That is the functional equation satisfied by the log derivative of the gamma function. Now where does this get us? Well, it will help you to determine what this function does for specific values of the argument. We know what gamma of 1 is, gamma of 2 is, gamma of half, 3 halves, etc. The question is, can I do the same thing for the psi function? And the answer is yes, you can, because this equation, this functional equation, also helps you to analytically continue the psi function. Once you give it to me in some region, this will help me, just like the gamma function did, to continue this, analytically continue this function. Now I have already pointed out that gamma of z goes like minus 1 to the n over z plus n factorial plus a regular part near z equal to minus n, near a pole, near each of the poles. This is the behavior of the gamma function. This is the singular part and that is the regular part. Now if you differentiate this and divide by the gamma of z once again, I differentiate this, I get a z plus n squared. So psi of z has the derivative of gamma function has a double pole at z equal to minus n plus a regular part. That part remains regular. I divide one by the other, it is clear that the derivative has a 1 over z plus n squared, the function has a 1 over z plus n. So this will immediately imply that psi of z goes like minus 1 over z plus n plus regular part. So the log derivative has a constant residue at each of the poles. It too has a simple pole at 0, minus 1, minus 2, etc. But unlike the gamma function, which has an n dependent residue, this function has minus 1 sitting here, just minus 1 as a residue at all these points. Now the question is, what does psi of 1 do, for instance? Gamma of 1 we know is 1, what is psi of 1 equal to? Well, the way to do this, you need a little bit more information. You need to know that gamma of z equal to, near z equal to 0, there is a leading term 1 over z, the singular part, and then the regular part, we need to know what the regular part is. Okay? It is going to be a power series in z, powers of z, starting with z to the 0 and then etc. etc. So this is going to be of the form plus summation n equal to 0 to infinity Cn z to the power n on this side, near z equal to 0, in the vicinity of z equal to 0. The question is, what are these constants equal to, which requires a little harder work. You need to start with a representation of the gamma function and work through to find out what the answer here is. But it is not altogether trivial. Turns out that the constant term C0 is known, all the terms can be systematically found out, but the constant term is a kind of universal constant. It is one of these fundamental numbers like e or pi or something like that. It is on the same footing, and it is the following. It is called the Euler constant, and it is defined as follows. It is denoted by gamma, and it is little gamma, and it is defined as follows. You know that if I took the harmonic series 1 plus a half plus 1/3 plus 1/4 etc. and summed it up. So I start with n equal to 1 to some capital N 1 over n. This series diverges as capital N tends to infinity, because the harmonic series diverges. It is infinite, right. The question is, how does it diverge? And roughly speaking, I have something like 1 over n to sum over, and that is like integrating over 1 over x up to some upper cutoff. Now what is dx over x? When I integrate, I get log x. So it is clear that this series is going to diverge very slowly, like the log of capital N, but as n tends to infinity, it definitely goes to infinity. The next question is, suppose I did this and then I subtracted from it this n here on this side, log n, sorry, the whole thing goes like log n. So I subtracted log n and then took the limit of this as n tends to infinity. So after I subtract the divergent part, is there anything else left over? Is it finite, or is it 0, or is it still infinite? It could still be infinite, because there could be a correction which goes like log n, for instance, and that would also diverge. Well, it turns out that in this case this has a finite limit. The limit is non-zero, it is finite, it is a positive number, and it is given by this thing here, gamma. That is the definition of this Euler constant, and its numerical value is found to any number of decimal places is approximately 0.5772 dot dot dot, etc. So it is clear that this number has a well defined value, but what is not known, what is conjectured is that this is an irrational number. In fact, it is conjectured that it is a transcendental number, not the root of any algebraic equation of finite degree with rational coefficients. So this number is conjectured to be irrational. Nobody has proved this. Proving the irrationality of given numbers, proving the fact that they are, proving the transcendental nature of the numbers, individual numbers, is a non-trivial task. Proving the fact that pi is transcendental took place only in the 1880s or something like that. Similarly for E, Hermite proved that E was transcendental, and gamma is another of those numbers which is believed to be irrational, but we do not know for sure. It would be a big surprise if it were rational. On the other hand, nobody has proved conclusively that it is irrational, but the chances are overwhelming that it is an irrational number of some kind. So it turns out that this is 1 over z minus gamma plus C1z plus etc. this side. So the gamma appears here in this place. Once we know that, we can ask what gamma prime is going to look like, and then of course we differentiate and divide etc. etc. It is not hard to show that psi of z minus 1 over z, because remember I said that it is minus 1 over z plus n plus a regular part, and the regular part again turns out to be minus gamma plus etc. So you put that together with this and let z go to 0, so this thing will imply immediately that psi of 1 is equal to 1 minus 1 over z etc., and this is a minus gamma. Okay. So if you let z go to 0 in this, the leading term, the pole cancels out and leaves you with just the constant there, and it is minus gamma. So this is another way of understanding what this gamma is. It appears all over everywhere, and a very interesting relation is that psi of 1 happens to be this minus the Euler constant here. Okay. That will of course immediately tell you what psi of 2 is. It is 1 minus gamma, and therefore psi of 3, etc. So all these numbers, every one of these numbers in psi of, you can write down psi of n plus minus gamma plus summation j equal to 1 to n 1 over j. Okay. You can therefore find, just as we found that the gamma function at the positive integers were all factorials of numbers, natural numbers. Similarly, this psi function at all the natural numbers is minus gamma plus something or the other. So lots of identities of this kind can be established. Okay. What else did I want to do? Oh yes, here is another representation for the gamma function where little gamma appears once again. I know that gamma of z is meromorphic. It turns out that 1 over gamma of z is an entire function. What's the reason? What condition should the gamma function satisfy in order that what condition should a meromorphic function satisfy in order that its reciprocal be an entire function? Meromorphic means in the finite part of the plane it has only poles of whatever order, it has only poles. And now I tell you its reciprocal is an entire function. What do you conclude? I mean, what condition should this function satisfy? No zeros. Can't have any zeros. If it has zeros, then of course the reciprocal will have divergences at that point, right? So it turns out 1 over gamma is entire. And entire functions have representations which depend on the zeros of this function. Just as you have a Mittag-Leffler representation for meromorphic functions which says these are all the pole terms and then there is a regular part which is an entire function. Similarly, if you give me an entire function, then it has got zeros at various points, and you could ask, suppose I tell you the points where it has zeros, and suppose zeros are at alpha, beta, gamma, etc., and you say, can I write it in the form z minus alpha, z minus beta, z minus gamma? Can I simply factor all these zeros together, multiply them together, and ask, is there a representation of this kind? And the answer is yes. There is a representation called the Weierstrass product representation which does precisely this, and in the case of the gamma function this turns out to be equal to, well, let me write it for let's write this. This is equal to z e to the power gamma z, where gamma is the Euler constant, and then a product n equal to 1 to infinity 1 plus z over n. Remember z equal to minus n is a pole of the gamma function, so the reciprocal will have a 0 at that point. So these are the zeros, and then it is multiplied here by e to the minus z over n. This representation is the so called Weierstrass product representation for the gamma function. Okay. And it is typical that such a representation will typically have portions which have the zeros and then e to the power an entire function like this. Okay. So it is a typical representative, a typical example of the Weierstrass product representation for the gamma function. Again, extremely useful. Now you could take logs on this and you could do all kinds of things, get other representations, etc. So that is the other thing I wanted to mention. Okay. Now let us go on. In the exercises I have given a number of other identities to be which are satisfied by the psi function, and you can work those out using the information given here. Okay, with that let us go over to beta function. Let me mention here that we have so far continued the gamma function analytically by this functional equation, gamma of z plus 1 is z gamma of z, and I did that strip wise. Arbitrarily far to the left you can do this by doing it strip wise. On the other hand, you can ask, is there a master representation for the gamma function, one single formula which is valid everywhere in the complex plane? And the answer is yes. It will involve a contour integral, so it is an integral representation, but it also involves multiple valued functions. So there are branch points, branch cuts and so on. So when we talk about multiple valued functions, I will come back to the gamma function and derive for you this other representation, but till then we use this functional equation as our main tool for continuation. Okay. Now let us go on to the beta function. Okay. Again due to Euler, in fact the integral is called the Euler integral of the first kind, and the gamma function is the Euler integral of the second kind. And recall what I said that you could define it for complex z and w to be equal to 0 to 1 dt t to the power z minus 1, 1 minus t to the power w minus 1, and you needed to have real z greater than 0, real w greater than 0. Okay. We need to derive a connection between the beta function and the gamma function, and the way you do it is to consider the following integrals. So consider the following double integral. Let us call that I of z and w equal to an integral from 0 to infinity du dv e to the minus u squared plus v squared u to the power 2z minus 1 v to the power 2w minus 1. You consider this integral. It is like the Gaussian integral I wrote down earlier. You got to ask, where does this guy converge? Where would this integral converge to start with? Infinity does not pose a problem because of this factor, but the 0 would pose a problem. So where is the convergence region for this? You want this exponent to be greater than minus 1, which is this region, real z greater than 0, real w greater than 0, the right half plane in each of these variables. So I start with this and I can do two things. One of them is to write it immediately. It is just a factored form, two integrals multiplying each other, and I can read off those integrals. So what I have to do is to put u squared equal to some variable. So let us do that and see what it gives us. So you put 0 to infinity du e to the minus u squared u to the 2z minus 1. So let us put u squared equal to t or something like that. So u is square root of t. So this is equal to integral 0 to infinity dt over 2t to the power half e to the minus t u to the power t minus a half. So this cancels with that, t minus 1, sorry, what am I saying, u to the t to the power z minus 1 and then a half this, but of course this is equal to 1/2 gamma of z. So on the one hand this is equal to a half from the u and a half from the v integral, so this is 1/4 gamma of u, what am I saying, gamma of z, gamma of w, quarter of each of these. All I did was multiply two gamma functions together. But you could also do this integral in polar coordinates, plane polar coordinates. So you set u equal to r cos theta, v equal to r sin theta, and see what happens. So let us do that. this is equal to, by the way, what is the region of integration in the UV plane? Zero to infinity, yeah, the first quadrant. So when I go to plane polar coordinates, little r will run from 0 to infinity, but theta will run from 0 to pi over 2. So this becomes equal to integral 0 to infinity dr, there is an r here, and then e to the minus r squared, which is this guy, multiplied by 0 to pi over 2 d theta, and then there is an r to the power 2z plus 2w minus 2. And then u is cos theta 2z minus 1 sin theta 2w minus 1, this fashion. Okay. So let us bring the r's together. This is r to the power, so there is an e to the minus r squared, and then an r to the power, well, let us leave the r here and write this as twice z plus w minus 1. This factor is out, and you have this, and there was an r dr times this integral. But r dr, if I had had a 2r dr and I put a half here, that is d of r squared, and I change variables immediately to r squared. So let us call r squared equal to something or the other, equal to s, for example. Then this is ds e to the minus s s to the power z plus w minus 1. But this is a gamma function, e to the minus s. Now that is gamma of z plus w. So we have on this side half gamma of z plus. So we have an identity which says half z plus w times that integral is equal to this integral, product of gamma functions here on this side. Now it is not hard to see that this guy here, if I put cos squared theta, so let us put cos squared theta equal to some new variable, let us call it z, xi or something like that, then says 2 cos theta sin theta with a minus sign equal to d xi, and this integral will become what? 0 to pi over 2 d theta. So this becomes equal to half gamma of z plus w. When theta is pi over 2, xi is 0, and when theta is 0, xi is 1, but there is a minus sign there, so let us make this 0 to 1 and get rid of that minus sign. There is an extra 2, so that gives me another 1/4 on this side, and then there is a d xi. So I make this a 2 here, multiply by cos theta sin theta, that gives me exactly d xi, so that takes care of this, and then it is xi to the power z minus 1, 1 minus xi to the power w minus 1. It is exactly that. But what is that equal to? That is the beta function, that is beta of z and w by definition. So it says this is equal to 1/4 gamma of z plus w, beta function of z and w. So that finally gives us a relation, a basic relation which says beta of z and w is equal to gamma of z, gamma of w divided by gamma of z plus w as an identity. So this tells you all about the analytic structure of this function. You can use this to analytically continue it. Once you know the continuation of gamma, you can continue it to all arbitrary values of z and w using this. So the entire singularity structure of this function is known to you completely from this identity. Okay. Very fundamental relation between the two Euler integrals. Okay. Now one of the consequences is the following. And I am not going to derive it, but I am going to mention it here. One of the consequences of this formula, and I am going to give this as an exercise, is if you put w equal to 1 over z, okay, then you end up with a relation which says beta of z 1 minus z equal to gamma of z gamma of 1 minus z divided by gamma of 1, which is 1. So you have a relation which says the product of these two gamma functions here, gamma of z gamma of 1 minus z, so it is a sort of symmetric product about the point half, about the line half, for instance. That is just a beta function here, and you can write a representation for this function here. Go back to the original integral representation and play around with that representation, and you can derive. I have given in the handout, I have told you how this should be done, what substitutions you should make. It turns out that you can show that this quantity is equal to pi over sine pi z. Not too surprising, because this chap here has singularities, poles at z equal to 0, minus 1, minus 2, etc., which is where this function also is singular, and it also has singularities. This one has singularities at z equal to 1, 2, 3, etc., and that comes from here. So as you know, the cosecant has got poles, simple poles at all the integers, and the ones at the negative integers and 0 are provided by this, and the ones at all the positive integers are provided by this out here. Now again you can take logs on both sides and differentiate. So you can get again a relation which will tell you psi of z minus psi of 1 minus z is equal to pi, and then if I differentiate this I take log and differentiate it. When I take the log I get a minus sign, so I have to get rid of that minus sign, so it will become psi of z 1 minus z minus psi of z on this side is equal to log pi, that does not get differentiated, and then I differentiate this log sign, so there is a 1 over with a minus sign, so it is minus, the minus I got rid of, so you have a sign in the denominator, you get a pi cos on top, so this is equal to pi cotangent pi z. Another identity, if you like, the reflection formula for the psi function. So there are a lot of these very beautiful relationships. Remember the last time we saw one of these relationships which said similar to this, we had a relationship for cosecant squared, it was 1 over z minus n the whole squared summed over all integer values of n. So this function will also lead, this identity leads to similar identities, okay, lots of identities of this kind. This formula, by the way, this formula here is called the reflection formula for gamma of z. Now the next thing I wanted to talk about was the doubling formula, and that is something which is once again, if you play with the relation between the beta function and the gamma function, you put z equal to w, then you end up with the following relation, beta of z equal to gamma of z over gamma of 2z. So bring this to that side and play around with this integral here, the explicit integral, and you can you can derive a formula which is called the doubling formula. So this will lead to a formula called for the gamma function, doubling or duplication formula, I do not remember which, for gamma of z, and it reads as follows. It says gamma of twice z equal to 2 to the power 2z minus 1 over gamma of half, which is root pi, not surprising because you get this by playing around with this beta function, and then there is a gamma of z plus half. Okay. A very, very useful formula in practice. There is actually a formula for gamma of nz, which n times this, which is written as a product of gamma functions of a smaller argument, but this is the most commonly used formula here, most useful one. Appears very, very frequently. So whenever you have these expressions involving Stirling's formula in statistical mechanics, this formula is very, very useful to simplify things. So notice in particular that if gamma is an integer, then this is a factorial, that is a factorial here if it is a natural number, and then this guy here will have a square root of pi on the right hand side, which comes from this formula here explicitly. Okay. Again, you can play the same game. You can take log derivatives on both sides. So, you take logs on both sides, you get log gamma of 2z equal to 2z minus 1, 2 to the 2z minus 1 times what? I differentiate this with respect to z, what do I get? What is the derivative of 2 to the 2z minus 1? Well, you can write this as 2 to the 2z minus 1 can be written as e to the 2z minus 1 log 2, right? So, you differentiate it and then you get the same factor up in the numerator, and then you must differentiate 2z minus 1 log 2. And if you do that, you get a 2 log 2, right? You get that term. So, let's take logs first, and then it's easier. 2z minus 1 log 2 plus log gamma of z plus log gamma of z plus a half minus half log pi. Okay. And now I differentiate, etc. So, you are going to get on this side, you are going to get a psi of 2z out here, 1 over this stuff here, and then I differentiate this guy with respect to this, and there is going to be a factor 2 on this side. That is equal to 2 log log 2 plus psi of z plus psi of z plus half. Okay. So, this is going to help us find things like psi of half, 3 halves, 5 halves, etc. We already found psi of all the integers by this recursion relation, and now we can find psi of half, 3 halves, etc. and there is an extra 2 log 2 sitting here. So, for instance, put z equal to half immediately. What do you get? I want to make sure that the answer comes out right. If you put z equal to half, you get 2, so let us get, so you get 2 psi of 1 equal to 2 log 2 plus psi of half plus psi of 1. So, this goes away, you have this. So this implies that psi of half equal to psi of 1 minus 2 log 2, and what psi of 1? We already discovered what it was, minus gamma. So this is equal to minus gamma minus 2 log 2. Check the signs, I am not 100% sure about the signs, I am just doing this off the top of my head, but just check out the signs here, make sure it is right. Okay. So you can now find psi of 3 halves, 5 halves, etc. They are all going to be similar to this with things added, but then you are going to have this minus gamma and then a 2 log 2 also sitting there. There are lots and lots of other identities. There are other integral representations also for 1 over gamma of z, etc. We will try to, we might come across one of them a little later on when we do multiple valued functions. I will give an integral representation for the gamma of z and also for 1 over gamma of z, the latter being an entire function. Okay. All right. So much for this. Now what is next? There are several identities between the beta function and the gamma function involving substitution of variables, changes of variables, etc., some of which I will put down in the problem sheets and hand over to you for you to try out. So that is about all I wanted to say about these functions. We will come back to these functions over and over again. In particular, this relation we had between the psi of z plus 1 minus psi of z is pi cot pi z. We will come back to that in a different context when we talk about Legendre functions, because there is a connection of this formula with the corresponding formula in the case of Legendre functions. But I will recall this formula to you at that time.